you for the opportunity to present my paper in the 16th edition of International Conference on Electronics, Computers and Artificial Intelligence. And the topic of my presentation is CNN-based heart rate classification using ECG signal without heartbeat detection for rhythm-aware health and emotion monitoring. Myself, Jomal Varghese Vadakan, and my co-authors are Dr. M. Shabbyamalai Manikandan and Dr. Lingareddy Sengaramati. This is the basic outline of my presentation. I will start with introduction, literature review, major objectives, proposed method, results and discussion, conclusion, acknowledgement and references. Moving to the introduction, the heart rate is an important vital sign in health and wellness monitoring to identify the various kinds of cardiac arrhythmias. For a normal human being, the heart rate varies from 60 to 100 beats per minute. The heart rate above 100 beats per minute is called tachycardia, and the heart rate below 60 beats per minute is called bradycardia. The heart rate variation leads to low or high blood flow to the different body parts, resulting in low or high cardiac outputs. These are different types of cardiac arrhythmias occur due to the variations in the heart rate. The heart rate is normally faster under severe physical activities and emotional stress. The automatic classification of the heart rate has become essential for health and wellness monitoring applications in addition to identifying various kinds of cardiac arrhythmias. The accurate detection of R-peak in bradycardia tachycardia conditions, visits, irregular intervals and long pauses is challenging due to the various ECG morphologies, noises and artifacts. The figure shows the different heart rates such as regular heart rate. Figure A and B shows the regular heart rate with the same type of QRS complex and different types of QRS complex. Figure C and D represents irregular heart rates with same type of QRS complex and different types of QRS complex, and the figure E represent long pause between R peaks. For heart rate classification, an essential step is to obtain the heart rate from the ECG signal having local waves such as P wave, QRS complex and T wave. The heart rate can be estimated using dominant spectral peak based heart rate estimation method using Fourier transform, autocorrelation based heart rate estimation method, and beat to beat interval based method or number of R peaks. The first three methods are effective when the rhythm is regular and normal local peaks, and the number of R peak based heart rate measurement method is effective for regular and irregular rhythms, but it demands accurate and reliable determination of R peak from the ECG signal. The heart rate estimation is still a challenging task because the ECG signals having different kinds of abnormal local waves and irregular rhythms. This slide represents the literature reviews we have conducted as a part of the research, and the heart rate can be in paper 8 it represents the heart rate can be estimated from the number of intervals and the average RR intervals, and in 12 represents the cardiac arrhythmias can be classified based on deep neural networks with an accuracy of 92.1%, and it outperforms the binary support vector machine, decision trees and multi-layer perceptron feed-forward neural networks. In paper 13, proposed a neural network based categorization of 4 major kinds of cardiac arrhythmias such as normal, bradycardia, tachycardia and block. In 14, it presents false alarm rate reduction method in intensive care units based on arrhythmia detection, and the famous Pan-Tompkinson's algorithm can be used to detect the R peaks, but not effective while detecting the wider or smaller QRS complexes, long pause between the R peaks and ventricular fibrillation cases. The major objectives of the paper are to present a 1D CNN based heart rate classification method using ECG waveform without R peak detection and classifying the ECG signals into slow rate, bradycardia, normal rate and fast rate tachycardia ECG signals without estimating the heart rate from the ECG signal, and develop a CNN based architecture with optimum hyperparameters in achieving better class-wise accuracy with a less computational load, and test the trained model using untrained ECG signals recorded using different ECG data acquisition systems and under different pathological conditions. The figure represents the block diagram of the 1D CNN based heart rate classification method using ECG signal, and it contains a pre-processing stage and 1D CNN architecture to obtain the trained model with the three classes of normal tachycardia and bradycardia. The pre-processing steps includes mean removal, which helps to remove the baseline wanders or offsets from the signal to improve the clarity of the ECG waveform and to enhance the accuracy. The amplitude normalization steps helps to improve the numerical stability, consistency of the data, and improves the training efficiency and model performance. And bandpass filtering stage, which helps to reduce the effect of different types of artifacts and noises present in the signal, and the prominent QRS complex is lies between 0.5 Hz to 30 Hz, and we are setting lower cutoff frequency as 0.5 Hz in order to remove the baseline wanders, patient movement artifacts and respiration artifacts present in the signals below 0.5 Hz, and we are setting an upper cutoff frequency in order to remove the power line interference and muscle noises from the signal. And this table represents the database information and the hyperparameters of 1D CNN model for heart rate classification. And here we are using a training database of MIT BH arrhythmia with a total number of 2460 segments, and each segment is 10-second duration, and each class contains 820 segments, and we are using a untrained testing database of for apnea, SLP and atrial fibrillation with a total segments of 80,465, and we have 5 convolution layers with a filter size of 32, 64, 128, 128 and 64 with a kernel size of 3 and a max pooling layer size of 2, and we are using an activation function in the convolution layer as ReLoop and in the output layer as softmax, and we have 3 dropout layers with a batch size of 16. So this figure represents the visual this figure shows the visual representation of CNN based waveform features using T-distributed stochastic neighbor embedding, which shows the CNN based features can be capable of distinguishing normal tachycardia and bradycardia segments. The training data set consists of MIT BH arrhythmia database. We are taking balanced database with 820 segments or 820 ECG segments from each class with the different PQRST morphologies, and the testing database is unbalanced with 10 seconds of duration, and from apnea ECG database we are considering about more than 50,000 normal segments and above 276 tachycardia segments and above 9,000 of bradycardia segments, and from MIT BH polysomnographic database, that is SLP database, we are taking above 7,000 normal segments and 100 tachycardia segments and 72 bradycardia segments, and from MIT BH atrial fibrillation database we are considering more than 7,000 normal segments, 1,526 tachycardia segments and 345 bradycardia segments. The table shows the class-wise and the overall accuracy of the untrained ECG database, and the result shows that the method had better accuracy for MIT SLP database compared to the other untrained databases, and this figure shows the confusion matrices for apnea ECG database, MIT SLP database and MIT BH atrial fibrillation database. The confusion matrix from the confusion matrix of apnea database, the class-wise accuracy of the tachycardia class is less due to the misclassification of tachycardia segments as normal due to the presence of noises, and the SLP in the SLP database the classification accuracy of the class-wise accuracy of the bradycardia is reduced due to the presence of misclassification of bradycardia segments as normal, which are normal due to the presence of noises, and the number of misclassified tachycardia segment as bradycardia, and bradycardia segment as tachycardia is 0. And in the case of atrial fibrillation database, which has a better classification accuracy for normal and bradycardia, as the normal and bradycardia when compared to the tachycardia segments. Then the tachycardia segments are classified as normal and bradycardia due to the presence of noises and the artifacts. And this table shows the performance comparison of the existing heart rate classification methods based on the R-peaks and deep learning networks. A fair comparison is impossible because of the evaluation results obtained from the different databases. But if you consider the CNN without R-peak detection method, for SLP database we are achieving a class-wise accuracy of 93.6%, and for tachycardia 95% and bradycardia 73.61%, with an overall accuracy of 92.74%. Conclusions: we presented a CNN-based heart rate classification method using ECG waveform without R-peak detection, and this model classifies ECG signal into normal rate, slow rate and fast rate ECG signals. And the CNN-based model was tested using untrained ECG databases recorded under different sensing devices and pathological conditions. The method achieves a promising result in the case of overall accuracy of 92.74% and 89.18% and 88.98% for MITBH polysomnographic database, apnea database and atrial fibrillation database respectively. Our evaluation study concludes that the deep ECG waveform feature-based heart rate classification method highly demands the creation of noise-free ECG signals, and in future we will attempt to develop a quality-aware CNN-based heart rate framework for reducing the false alarms. Acknowledgement: the part of the research work was carried under the sponsored project of Indian Council of Medical Research. These are my references. Thank you.